Good morning and welcome everybody. It is truly a distinct pleasure for me to introduce today's speaker, Professor Tamer Basar from the University of Champaign, who will talk to us about inducements of behavior via soft policies. I will be quick because the list of distinctions is truly very, very long. Dr. Basar received his bachelor's degree from Roberts College in Istanbul and then his PhD from Yale University. He served as professor in a number of roles and an administrator of the Institute of Champaign since 1981. He's a Swanland Endowed Chair Emeritus. He's a CAS Professor Emeritus and Research Professor still serving. He served as Director of the Center of Advanced Studies, as Interim Dean of Engineering, and Interim Dean of the Beckman Institute. Dr. Basar is a member of the National Academy of Engineering of the USA. He's a Fellow of the American Academy of Arts and Sciences and a Fellow of a number of professional societies. He has served over the years in very distinguished roles as President of IEEE Composition Society, the founding President of the International Society of Dynamic Games, and as President of the K2C2 Council. His work has been recognized by a few awards, that's sarcastic. The IEEE CSS Boni Award, the Quattro Medal from IFAC, the Bellman Control Heritage Award from K2C2, the ISDG's ISACS Award, the IEEE Control Systems Field Medal, the Medal of Science of his country of Turkey, the IEEE Medal and Medal, and the Wilbur Cross Medal from his alma mater Yale. He also honorary doctorates from KTH in Stockholm, from Tsinghua Shandong in northeastern China, Mogadishu University in Turkey, and the National Academy of Science and Technology. He also served, beside all of this, as editor-in-chief of Automatica, the leading journal of IFAC for a long time. And throughout all this, of course, he's made landmark, the groundbreaking contributions in systems and control, communication optimization networks, and as the landmark book on dynamic games. Having said all that, Tamer, it's a great pleasure. Thank you for your visit. Welcome.
Thank you very much, Francesca. It's a great pleasure to be here. I have been to UCSB several times on different occasions, and it's really great to be back. So I picked a title which is somewhat also current with the current political situation as well. I don't know what your political affiliation is, but how can one induce behavior of others? And the important thing here is through soft policies, which means that these are not threat policies. We know that, especially at the present time, threat policies are also, but it's not interesting mathematically. So I'm going to talk about a mathematical theory of inducement, and we can use different terms for this. Some social terms are like persuasion, which is act of causing people to do or believe in something. There's inducement. So these are all from the Oxford dictionary. Inducement, it's a thing that persuades or influences someone to do something. And more or less the same thing as persuasion. Incentivization, and I'll be using the word incentivize quite frequently, which would mean attaching a reward to a given behavior or threatening a penalty, but a soft penalty for failing to do that behavior. And we'll see how that can be formulated in mathematical terms. And also enticement is another social term that's used in this context, something that's used to attract or tempt someone. So if you want to develop a mathematical model to capture all of that, it's the first thing to realize or recognize is that it's a decision-making problem. It's a game. There are at least two actors. When you talk about influencing, there will be one decision maker who will be influencing the decision-making process of the other one. And there could possibly be multiple on the receiving end, or multiple influencers, or a mix of the two. So I have a recent paper, actually. If anyone is interested, I can send you this, where I discuss two types of inducements, which I'm going to discuss here. And so the two types are the following. The first type is a direct input by the influencer into the utility of the other party, and by shaping their objective functions. And to give examples of this from the real world, electric utility companies, for example, they may have scheduling policies, and you pay depending on when you use electricity, whether weekends or after hours, and so on, when you do your laundry, and you pay based on that. So the electric utility company will depend on the scheduling and the payment schedules for different times of the day or of the week, and then this immediately impacts the objective function of the individual consumer. Now, a second type is one where you control the information flow. The influencer has some information which the influencee on the receiving end would like to know, but then they don't have aligned objectives, and so therefore the influencer will control the flow of information by reshaping that information, and so therefore does shape the belief formation process. And this is would have applications, and we hear a lot on misinformation, disinformation, and so on. How can you distort, or deception also is part of that. How can you distort the information so that the other side will believe in something which is closer to the benefits of the influencer? Now, both of these actually lead to dynamic stackable games. And in this case, in game theory, if you have two agents, then you have essentially two different solution concepts. One is Nash equilibrium, one is Stackelberg equilibrium. And in this context, when you have this asymmetric roles of the two players or the two agents, then the Stackelberg formulation makes most sense. And in this case, in Stackelberg formulations, you have a leader and a follower. The leader comes up with a policy, and by taking into account the response of the follower, and they have different objective functions. And the question is, how can the leader formulate his policy in that context? So the influencer in this case is the leader, and the other party is the follower. So let me go a little bit into detail on these two types of inducement mechanisms. The first type, again, is where I gave the example of electric utility companies. Another example would be taxation, for example, policies for the government. You shape the followers, F's, utility function. So here you have a leader. The leader is the agent in red color, and the follower is the agent in white color. And the leader has the ability to impose her policy on F. And then the F optimizes his objective function under this policy. And the question that's raised here is how can one shape F's objective function? Again, note that there is an input going into the objective function of the follower by the choice of the leader. How can that be shaped to align it with the leader's overall objective to achieve an outcome, which would be favorable to the leader? And the leader will have full anticipation of the follower's response. Now, we have more recent work, which I'm not going to discuss here, where the follower's response may not be totally known, completely known to the leader. And in that case, then you have to bring in learning schemes and view this in a repeated framework. Now, the sequence of moves for this type 1, to make the problem precise, is that the leader announces a policy. Let's call it gamma sub L. And it depends on the action of the follower. I call it U. So whenever I use lowercase u, it corresponds to actions. Subscript F means the follower's action. Subscript L means the leader's action. And the policies are denoted by gamma. And so there is some common information, Z, that both sides observe and know about it. And there is some private information, Y, for the leader. So therefore, the leader's policy depends on the action of the follower, as well as on those two random variables, Z and Y. So given this, given that the leader uses gamma sub L, the follower optimizes his resulting objective function and arrives, so again, the objective function of the follower has to depend on the policy of the leader. Again, remember, recalling this example on the taxation policy and the electric utility companies, pricing schemes, and so on. So the follower optimizes the resulting objective function and arrives at an optimum policy, which is a function of only the information that's available to the follower, which is this Z. And then the last sort of step, or the next to the last step, is that L will execute the action. This is collecting sending a bill, for example, in the case of electric utility companies, and then receiving payments, executes the action, which is based on the action of the follower in response to gamma sub L, and then depending also on Z and Y. So you essentially, on this announced policy gamma sub L, you replace U sub F with U sub F star, which is the optimum response. And then as a result of this, you have UF star and UL, and both L and F, they receive corresponding payoffs. You have to take expected values and so on. So in this case, I have this note here that I have added that the fact that gamma sub L, the leader's policy, depends on U sub F, gives the leader additional freedom to be able to shape F's preference. So therefore, this is the case where the cost function or the objective function or the reward function of the follower depends on what the policy of the leader is, because the leader's policy depends on the action of the follower. So you can, even if you have a quadratic cost function, for example, if gamma sub L is not linear in U sub F, then you end up with a non-quadratic function. So I'll go deeper into the type 1 inducement, but let me just talk about at a high level on the type 2 inducement, which is shaping the follower's beliefs. So there is, in this case, the leader has access to some information of interest which the follower is interested in. And the only way the follower can find about this is over a channel which is impacted by the leader. The leader actually reshapes that information, and that information flows through signals to the follower. So the question in this case is, how can the leader craft the information of interest to induce the receiving agent, in this case, again, the follower, to perceive it as desired by the sending agent L, even when the follower is aware of the relationship between the received signal and the information of interest. So what's the best the follower can do in this case, and whether the leader can reshape that information in such a way that it will benefit him rather than the follower. Okay? And what the follower will do with this is a separate question. So this is known in the literature also as strategic information transmission, SIT, and it has connections to acts of deception and also the spread of disinformation, as I indicated earlier. So again, you have, in this case, for this scenario to make sense, you need two agents, at least. There might be more than two. For example, the information of interest may be accessible partially by more than one agent, and they are all trying to influence the follower or followers. And so it's an asymmetric information, and there's misaligned objectives in this case. So one thing, when we talk about deception, there's a difference between deception and pure lying. So any mathematical modeling of the process of deception has to account for the fact that deceptive signaling is beyond pure lying. Because if it's pure lying, then that can be detected, and the follower may decide to do something totally different and not take it serious. And it's not obscuring the information of interest. That's not sending it at all. So it's you have to manipulate it and reshape it in such a way that the follower will not have anything else to do but rely on that as the true information. And so deceptive signaling is actually controlling the perception or the belief formation process at the follower's level, and making the receiver side act in line with the intentions of the sender of information. Just one anecdotal thing. So the question, Lithuanians were besieged by disinformation from Russia. This is from The Economist in 2019. And they were talking about developing lie detectors. How can you detect misinformation? How can you detect things which are blatant lies? And I'm not sure how successful they were, but anyway, it made The Economist as an important sort of an issue at the time, and still this persists. So what are the sequence of moves paralleling the ones for type 1? So the leader has access to realization of a random variable, say Z, and it could have two components, X and Y, where X is the information of interest to the follower, and Y is some private information. So when the leader reshapes Z, he has to make sure that the private information will not leak to the follower, even though they may be correlated, but only the other X, which is the information of interest, is reshaped. So the leader generates a signal S, in this case, using a policy which depends on Z, which is possibly stochastic, and he has to anticipate F's optimal response, and in response to that signaling policy. Now note that in this case, the way the follower's decision-making process is affected is not by influencing, impacting the objective function of the follower, but by impacting the information that the follower will be based on. So that's why it's different from the type 1 type of inducement mechanism. Now, if the follower receives S, or receives, if it's a noisy channel in between, noise-corrupted version of it, let's say S prime, and will select a policy, gamma sub F, that optimizes this objective function. And as a result of this, both L and F receive corresponding payoffs. Now, depending on the choices of the objective functions on both sides, this framework captures problems of deception, as I said, transmission under privacy concerns, that is, if X and Y are correlated, the way Z is shaped will transmit only information on X and not on Y to the extent possible. So there may be a constraint on the privacy. And this leads to a quantification of persuasion capability of the sender. Okay? Now, this is a control group, control community, and one example of this would be you have multiple sensors, and the sensors send measurements to a fusion center on some random variable X, which is useful for a control system, for example, or it could be a random process X sub K. But then there is an intruder, an adversary, who compromises this. So the adversary, in this case, plays the role of a leader who reshapes this process, X or X sub K, and then wants to deceive the receiver, which will be the controller, by injecting bias into the measurements, say some theta, and doing this possibly selectively in a multiple sensor set. Okay? So this scenario is not necessarily only one of information transmission, but also one of control, where sorry for that. But also one of control, where the controller ends up sending a bias signal to the plant. So in that case, the controller takes the role of a leader. So there are many other application scenarios. So what are the parallels between these two types of inducement mechanisms? The type 1 is the ideal scenario of L getting the best she can, corresponds to a mechanism design problem. And mechanism design has been an important area of research in economics for many years, starting in the late 70s, early 80s. And so in this case, the leader makes the follower face an optimization problem, which is totally aligned with her interests. That is, the leader reshapes the objective function of the follower toward her goals. In the type 2, it's a parallel situation, again an inducement mechanism. This is strategic information transmission, where the sender of information aims at having the receiving agent act based on the distorted or biased information that he receives, in a way aligned with the objective of the leader. That is, you are controlling the perception of the receiving agent toward her intentions. Okay. Yes.
So, but we are in the context of a Stackelberg game. So
yes.
That the follower knows the mechanism by which information is being manipulated.
Yes, but does not know the realization of that. Right.
But we'll know the basic.
Of course. Yes. It's a perfect knowledge on the rules of the game, and on the policy of the leader.
And on the prior as well, right?
Yes, on the prior as well.
So your example of the control signal system doesn't sound very likely, because to mean that the controller knows the way in which the attacker is sort of manipulated.
No, well, yes, but you cannot, if you rely on the information coming from the sensors, even if you know how the attacker is manipulating that information, You know a mapping, for example, a nonlinear mapping and so on. But you have to use that because you have nothing else other than prior. If using only the prior information gives you a better outcome, then you can use that. That's part of the policy. You can always ignore what you have received.
Right, I understand that. What I was saying is that imagine that you know the function that the attacker is using.
Yes.
That is a little bit,
Well, yes. You can compute it. I mean, in this case, both sides can actually compute the gammas. And so therefore, because it's a full information now, there's more recent work where you do not have full information, you have to do learning and so on. But if it's full information, both sides can compute it, but that's what they can do. That's the best they can do. So here is a more precise mathematical formulation for the type 1 inducement. So you have the state of nature, which is a random variable or random vector x. L observes y, and F observes z. So again, the x corresponds, has both y and z. So they are both correlated with x, and L also has access to z. Okay, so the important thing here is that the leader has access to the information that the follower has access to. But on the top of that, there may be some private information that the leader observes, which is y. The action variables are, for the leader, it's a function of y and z, and for the follower, it's a function of z. In other words, there is additional information that the leader has access to. And it's not that important, actually, as we are going to see in the theory. Even if there is no y there, this is still a very valid formulation. Now, the important thing here is that the leader also has access to U sub f, the action of the follower, again, as part of a Stackelberg game, and can use it in constructing an incentive policy, which is a function of yz as well as of uf. You have the loss functions given, and this is common information to both sides, which are L is the loss function for the leader, L sub L, which depends on both UL and UF as well as on X. And the follower's cost function also depends on UL, UF, and X. Now, if UL does not appear here, then the problem is not interesting because there is no way the leader can induce a behavior on the follower. And of course, you have these are random quantities, so you have to take the expected, look at the expected cost, take the expectation of these over both, over the random variable x. Later, if I have time, I'll discuss the cases when the leader and the follower have different perceptions of the probability distributions on X. And so there's a discrepancy in the probabilities, and that can also be handled, but I'm not sure whether I'll have time. So what's the immediate sort of direct approach to this problem? We're looking for a Stackelberg equilibrium. So you announce gamma sub L for the leader, and then you see what the response of the follower is going to be. So let me call it R sub F of gamma sub L. Let me assume at this point that this is a unique response. Otherwise, it will be a reaction function, and you have to do an optimization over the reaction function. But let's, for the sake of discussion here and simplicity, and you can actually have various sort of special cases where that uniqueness assumption holds. Now you minimize, you replace the for the follower's response to gamma sub L, and you substitute it for U sub F, and then minimize J sub L, because the the leader will anticipate what the follower's reaction will be and come up with the best policy, gamma sub L, taking into account that reaction. And let's say that this minimization problem admits, and I'll have give conditions under which that holds, gamma sub L star. Then the Stackelberg solution in this case is gamma sub L star is the policy, incentive policy for the leader. And when you substitute gamma sub L here into gamma sub L star for gamma sub L, the optimum, and this is the reaction function, this is what the follower's action is going to do. Now, the main challenge, even though mathematical formulation is fairly straightforward, the main difficulty here is that the computation of RF gamma sub L, note that gamma sub L actually depends on U sub F. So the structure of the optimization problem faced by the follower depends on the policy of the leader. And that makes it a very complicated optimization problem because this structural dependence. And for example, maybe the best policy for the leader is a discontinuous one. Maybe the best policy for the leader is, even if you have a quadratic cost function, it may be a nonlinear function. And so therefore, this makes the optimization problem faced by the follower depend very critically on the choice of gamma sub L. And you don't know ahead of time what gamma sub L is. So this structural dependence essentially says that this direct approach to the problem is not a viable one. Now, an important observation here is that a bound, the question is, can we obtain a lower bound on the Stackelberg cost and come up with a policy which will actually make that lower bound tight? So a lower bound is one where, forgetting about the follower's cost function, objective function, let's assume that we have the scenario where both the follower and the leader optimize in cooperation the leaders under the same information structure, the leader's cost function. Okay? Definitely the leader cannot do any better than that. Okay? So this leads to an indirect derivation, which is the following. You find the optimum team performance for L, for the leader, with F fully cooperating. Okay, so let me call this, and this is in the original information structure, without the leader's policy depending on the action of the follower. If you allow it to depend on the action of the follower, you cannot do any better than this anyway, because the leader has access to all the information the follower has. So let me call this by FLT. So this T stands for team. So the two of them act as a team. And so you obtain, let's say that you have a unique solution here. Then the leader has an extra sort of information, which is in his policy, which is the action of the follower. So this redundancy of information, this brings in, and this is a very crucial thing, it leads to a rich set of solutions, gamma L. So now I come up with a gamma sub L, which depends also on the action of the follower, which will lead to exactly the same performance. If I can find such a gamma sub L, which takes into account now the follower's response, then that will be the Stackelberg equilibrium. Okay, so one that if I bring in also dependence on V here, and a policy for gamma sub L that we're looking for, this is a side condition, is one where when you substitute for U sub F, this policy, F sub F T, as a function of Z, and then this policy is a function of Y and Z, gives precisely this FL. And one class of such policies is one where you take this FLT, which is a function of Y and Z, and then add a function of U sub F, which vanishes when U sub F is equal to F sub Ft. Okay? And so then the incentive design problem in this case is one of finding gamma sub L star such that the following two side conditions hold. One side condition is that F sub T minimizes this quantity. Now we bring in the follower's cost function. You find the response of the follower to this announced policy for the leader. And then the leader's policy satisfies this side condition when the follower's response completely matches the team solution. And clearly, when I showed I had this function of G, if these side conditions are satisfied, then this is a very rich class of solutions. And in fact, we can show that there exists at least one such solution under very reasonable conditions. And in fact, there are multiple solutions, and which then opens the door for additional specifications, such as robustness to inaccuracies in knowledge of problem parameters. Okay, this goes back to a paper that I had written in 1984 in SciAm, and which shows that under very reasonable conditions, Fresher differentiability, weak continuity of Fresher derivatives, strict convexity of L sub F does not have to be quadratic in UF. This is important because you need a solution to that optimization problem. And you have a Hilbert space of policies. Then there exists such a policy, gamma sub L star, which is linear in U sub F. So even though the problem does not have to be quadratic, using a linear policy, you can do it. And the main tool in proving this, and here, this is your G function that I had, and this is a linear bounded operator, Q sub Z, which has to satisfy this equation. And here is where I need Fresher differentiabilities. And the main tool is the Hambana theorem, in this case, separating hyperplane. Okay, so there's a rich class of policies. And as I indicated, Q sub Z is generally non-unique with possibly nonlinear dependence on Y and Z. And for example, if you have a linear quadratic game, as a Stackelberg equilibrium policy for L is this one, where lin means linear in YZ. Okay. It shows nonlinear dependence on Z, as you can see here. So you can extend this to multiple induces. I have in an economics paper in 1989, I have this with multiple followers and multiple decision hierarchies. You can have intermediaries, and there could be, if you have some hierarchical scheme, you have an intermediary. The intermediary plays the role of both as a follower as well as a leader in this case, and you can have the inducement propagating down the hierarchy. And I mentioned earlier that if you have different probabilistic outlooks for L and F, then you can still work. I don't have time to go into that. You have to take into account, here you'll see superscripts F and L, and this means the expectation with respect to the distribution, that perception of the follower, L is with respect to the perception of the leader. And the details, if anyone is interested in, I have a paper in the CPHS, which was presented in December, which discusses this. And there are, again, multiple solutions in this case, and then one can show existence. And not uniqueness, but so I'm going to discuss, I'm running out of time, so let me talk about the inducement, the second type of inducement. I'll just give you a few references, and then, because I don't have time to cover this. Again, this is a slide I had earlier. How can you craft the information of interest to induce the receiving agent to perceive it as desired by the sending agent? And this is a non-cooperative game, again. And this problem, so there's a lack of cooperation, and you can, this is strategic information transmission. It's you can do a Nash equilibrium, which in my opinion does not really apply to this, but some economists have looked into that. And the Stackelberg equilibrium is what we are really interested in. And these lead to structurally different equilibrium policies. And so here is just to give you a precise mathematical formulation. And this is something those of you who are in information theory or communication will notice this as like a Gaussian test channel, where you have information coming into the encoder encodes it over a noisy channel, and then you have the receiver has the decoder, and then you come up with an estimate of whatever you are interested in, of x or x and theta jointly, and so on. And in that scenario, in the standard information theoretic framework, you have the objective functions are the same. So these are, even though it's a problem with non-classical information, you have both the sender and the receiver are interested in minimizing distortion at the receiving end. Okay. Now, in the strategic information transmission, as I discussed earlier, this is not the case. They are not working in unison. They have different objective functions. So the sender in this case wants to distort the message in a way. The message of interest to the receiver is x, and theta is a private parameter. So here are the objective functions between the receiver and the sender. The receiver wants to estimate x given the measurement y, and knows what these mappings are, G and H. And what the sender does is he wants the receiver not to estimate x, but a biased version of x, where theta is the biased parameter. Okay, and which is private to the sender. So this is a problem with non-classical information and so on. It's fairly complicated to obtain the solution. I mentioned an early work in economics, Crawford and Sobel, in econometrica, but they looked into the Nash equilibrium solution, and that's not what we are interested in. And they said the best way with a clean channel, not noise, and they said the best would be a Nash equilibrium, which is not unique, is one which is non-injective, where these maps are quantized-based. In other words, the sender has to introduce some uncertainty into the process, and that uncertainty is achieved through quantization. Now, for the Stackelberg equilibrium, we looked into this problem initially in an IEEE proceedings paper in 2017 with Emre Akyol, who was a postdoc with us, and Cedric Langbord, my colleague. And what we showed is that for the quadratic Gaussian case, that is when X is Gaussian and W is Gaussian, and jointly independent noise, the Stackelberg equilibrium is essentially unique and linear with and without channel noise. Okay? So you send a linear version of X, but a distorted version of X. Okay? So, well, I have, if anyone again is interested, I can send you the paper, and note that this is the case where the noise variance is 0, so there is no noise. So you take X, and then you add on it, you distort it by an amount A times theta, where A is computed this way, which takes into account the follower's response. Okay, and in the noisy case, it's again a similar type of a thing, but then you scale it up or down in order to compensate for the noise. Okay. So the proof. Now, one thing I want to for the first type of inducement, Hambana theorem was the main tool. For this one, it's a totally different set of tools. It's you use the maximal correlation coefficient property, and essentially you do an optimization in the space of posteriors, and then you show that this is a bound, but it's a tight bound. Okay, so I'm not going to go into this. There is a multidimensional version of this, what we did in that paper. So with a former student of mine, Mohamed Sayin, we have a transactions paper on this. The thing is that this leads to a non-convex optimization problem, which we had to find an indirect way of solving. Yeah, and another extension, you can extend this to multiple stages, and then there's an important sort of quote from Abraham Lincoln. It says, "You can fool some of the people all the time, all the people some of the time, but not." You cannot fool all of the people all the time. So that's the question is how much you can gain by going to multiple stages, multi-stage transmission, and what you can do if there are multiple receivers. What fraction of them can you deceive? Okay, several papers again here. So let me conclude by saying that I have discussed two types of inducement mechanisms, and they require totally different approaches, and they are both non-standard for these problems. A problem of interest, which some of my students are looking to, is a mix of the two. In other words, can you have scenarios where both the objective functions are impacted, of the follower are impacted, as well as the information transmission. You are reshaping the information on the relevant random variable. Now, these two, if you consider these two problems independently, they require different tools. So what sort of a tool mathematical tool you can bring in. And so any powerful incentive design mechanism will require redundancy of information. And this is what I would call a monitoring scheme. And so all these taxation policies, electric utilities, and so on, they have redundancy of information because you can monitor whether the other side, the receiving side, is acting the way that you have. If they cheat, for example, on taxation, then they could be caught. And the non-uniqueness of such policies can further be exploited to benefit robustness. And one important study that we currently have is, what if you go to a very large population of receivers? Then the monitoring mechanism is not that easy. How can you monitor? So you have to monitor a fraction of them at random, and that we have some results on that as well. And so the second type of inducement, shaping perceptions and beliefs, is again leads to a non-standard, non-classical stochastic optimization problem, and solutions in this case require a judicious tight bounding of achievable performance, extending this to networked agents and bringing in robustness through risk sensitivity are current sort of directions of research. Okay, so I'll stop here. A few other recent extensions that we have, some papers to appear in the transactions and of automatic control as well as control of network systems. And these are all inducement relevant. And how can you disclose another, the third one here discusses, which is an ACC paper from last year. How can you disclose information strategically in a multi-stage problem when the timing of disclosing information is, again, another interesting problem. And random monitoring, I mentioned this, so we have a paper at the IFAC Congress. Okay, thank you. I'm sorry for this.
I was going to ask about kind of the multiple sender regime.
Yes.
It was, I think, the first paper that you
Right.
highlighted on your list. Could you comment on kind of what kind of the overarching story is?
The overarching story there is multiple senders, and let's say that you have a single receiver, and you have two different bias parameters, theta 1 and theta 2. And one of the senders, now, if you have two leaders and one follower, yeah, then you have to assume a certain solution concept among the leaders. If you have one leader and multiple followers, you have to assume a certain solution concept among the followers. So we are assuming Nash equilibrium in that case, which is a natural thing. And so therefore, both of them, they have different, the senders want to force the receiver to think in different directions because their objectives are not aligned. And the question is, what can one do? And we have results which show that as you increase the number of senders, the receiver actually benefits when the sender are playing a Nash game among themselves, because they cannot agree unless they agree on the same bias parameter.
So the presence of other senders in an environment minimizes
benefits the receiver generally.
So it
Yes.
hurts the sender.
Right.
I have a question, but it's a very loosely stated question, Tamer, forgive me. So you have described these persuasion games, soft persuasion games, in a wonderful, deep mathematical way with the multiple setups and so forth. And then ultimately the problem ends up being very difficult, right? I mean, you have this highly complicated, first setup, you have to use the Van Hand theorem. And
but linear policies. Easily implementable.
So my question is, we live in a world where we do try to influence each other in some ways.
Sure, of course.
Psychologists and sociologists and communication scientists have studied versions of these problems from very different angles. So is there, and as you know, in our community 10, 15 years ago, there was an explosion of interest for consensus algorithms because they were a wonderful intersection between what sociologists, psychologists, and we could literally build bridges between these communities. So, are there any? So having said all that, are there any simple phenomena that social scientists have identified that you can recover with this mathematical thinking?
We have a mirror. This is for the type 2
the type 2. That's not
persuasion. We have a mirror where we have one psychologist on our team, and we are conducting experiments with groups of students,
Right, right.
telling each one a distorted version of
Distorted
some
signal, okay.
information,
Yes.
and how the response is going to be.
Right.
And so that's an ongoing research. Yes.
Well, best of luck. All right. Any more comments from the audience? I don't see any of them, but Dr. Basar will be with us for the rest of the day, and I think we all have various appointments with him. So with that, I'd
Sure.
like to thank